Hi, I'm Tsung-Han Wu from National Taiwan University. I'm presenting our work D2ADA, a general active domain adaptation framework for semantic segmentation. We first introduced the background and our motivation. In the field of domain adaptation, a trade-off exists between performance and annotation effort. In order to strike the balance in this trade-off, we explore the possibility of active domain adaptation, ADA. In this framework, we aim to maximize the performance by querying least target domain labels. In the ADA scenario, queries from both exploration and exploitation are important. The exploration method reduces the domain gap by selecting diverse data in the target domain, while the exploitation method selects data with high model uncertainty to fine-tune the decision boundary. In this work, we introduced the dynamic density-aware active domain adaptation. First, our density-aware selection solves the problem of existing exploration method with theoretical support. Second, our dynamic scheduling policy adjusts the labeling budget of domain exploration and model uncertainty, further improving the labeling efficiency. We later introduced the two components respectively. To achieve efficient target domain exploration, we introduced the term domain density. Considering the scenario of region-based labeling, we first obtain region features and category for all samples. Then, we use GNMs to estimate the categorical domain density for source and target domains. Here, we take traffic sign as an example. The second step is density-aware ranking. For each unlabeled target regions in the same class, we query its domain density with the GNMs. Then, we rank this region with the proposed matrix pi in a descending order. Our key idea is to select regions more prevalent in target to achieve efficient exploration and to choose samples that are observable in source to replenish model's knowledge. We then explain our method from a theoretical aspect. The bound of domain adaptation includes training loss and a domain adaptation term, which can then be organized. As the divergence of the two priors are similar, we only consider the latter term. Then, the chiral divergence can be approximated by a Monte Carlo process, turns out to be highly correlated to our pi matrix. So, by labeling regions with large pi value, domain shift can then be reduced, and thus makes the bound tighter. We also develop a class balance selection. We observe models can easily reach high performance in some classes but struggle in others. As domain gaps vary by classes, we spend more budgets on hard classes while few on already well-aligned ones. In practice, we apply the interclass weighting for each class C as the equation. Next, we describe the dynamic scheduling policy for the ADA problem. Initially, lots of high-confidence errors exist due to large domain gaps. As shown in the diagram, we need more exploration in the early stage. Then, as the domain shift reduces, high-confidence errors are replaced with low-confidence ones. Thus, we require more exploitation methods to refine the model in the late stage. We develop a simple budget allocation strategy to achieve the goal. Given a constant labeling budget, we allocate more budgets for domain exploration while less for model uncertainty at the beginning. Then, we gradually schedule the two budgets with half decay controlled by a hyperparameter lambda. Let's show our experimental results. In the two benchmark, our method hugely surpassed existing active learning baselines. Besides, our method outperforms all existing domain adaptation methods. With 5% target labels, we achieve over 97% of the target full supervision upper bound. We also visualize the labeling distribution of selected regions. It shows that our method indeed selects more labels on hard categories, but less on easy ones like roads and building. Let's summarize our work. First, our density-aware selection opens up a new way for the ADA problem. Second, our novel dynamic scheduling policy balances exploration and exploitation. Third, our method achieves state-of-the-art performance on the two benchmarks. Thanks for watching.